this lesson, we're really looking at the difference between accuracy and precision and how we can indicate or quantify each. As I'm sure you realized after reading the article, accuracy and precision are not two words for the same thing. There are definitely differences between them. Accuracy tells us how correct we are. Accuracy tells us how close to the target we hit. Accuracy really just tells us whether or not we're right or wrong based on an accepted value, what we should have gotten. Precision has two definitions. Precision can absolutely refer to how clustered our repeated measurements are. We take multiple trials and we just look to see how close they are to each other. But precision can also deal with how exact our number is. So again, accuracy, correctness. Precision can really refer to either reproducibility, how close, or how exact a number is written out. And right now, because we're looking at significant figures, we're really going to focus on precision and the definition of precision that deals with the exactness. That's what significant figures really tell us. And really, the reason that significant figures are so incredibly important and why precision is so incredibly important is because when you're looking at science and you're looking at taking measurements using different instruments, precision costs money. I drew a picture of a beaker, and the beaker has these increments, or the smallest lines, at every 10. The beaker maybe costs $10, whereas a graduated cylinder, if we drew it a little bit higher, we could have actually had it hold the same amount of volume. You notice that the walls of the graduated cylinder are a lot smaller than the walls of the beaker. That allows us to report a more precise or exact measurement of volume without having to worry with as large of a meniscus error. And because the walls had to be pulled out a little bit thinner in order to get that preciseness, the graduated cylinder that holds the same volume will usually be at least twice as much as the beaker. Precision costs money. If I really wanted a precise measurement, I might even use something called a burette. And a burette, I'll show you the next time you're in class, is a really, really thin, really, really long tube that actually drops the volume from the bottom here. It has a valve here that allows you to open and close it. But these walls are so thin that we can actually get even tenths of milliliters out of there. We can go drop by drop, literally. And something like this might cost $50 or $100, whereas this might be 10 and this one might be 5. Precision definitely costs money. And the idea of taking measurements to the appropriate amount of precision, reporting to the correct number of significant figures, really tells to the scientific community how much money you are using in your instruments, which then will tie into the reproducibility and how closely other people can get your results. Precision costs money, you don't want to lie. So anytime you're taking a measurement, you always record all of the numbers up to the smallest increment and one estimated digit. So that's all known values and one estimated value. That's the rule of taking measurements that we'll be practicing in our lab. So for instance here, we know that these are tens values, 10, 20, 30, 40, 50. And if you think in terms of where a 10 is, when we write a number out, the tens place is here, which means our estimated digit would be the next one. So we would estimate the ones place using this glassware. Here, since this is 10, 20, 30, we know we have these little lines every 1. And since now we have our measurement known to the ones place, our estimated digit is in the next place value, we would estimate 1 decimal or the tenths place. If we were using this one, where maybe now we know the tenths place, we have to estimate the hundredths. And if we have incredibly precise equipment, a lot of our balances, that maybe give you a line in the hundredths place, you would estimate the thousandths. But the rule is always that you write down all your known and exactly one estimated or unknown value. And those numbers that you write for your measurements, that's what becomes your significant figures. So significant figures are all known and one estimated or unknown value from any analog device. Your digital balances, your digital thermometers, whatever numbers that they report, those are automatically your significant figures. You do not estimate another digit on a digital balance, but you always estimate it on anything that's not digital. So now that once you have your actual measurement written down, you can report it to others. And other people will now know how many significant figures you had based on what you wrote down. These are the rules of significant figures. We need to consider non-zero number, captured zeros, leading zeros, and trailing zeros. And these are the rules that people kind of get hung up on. But my goal for this year is for you to really understand why these rules apply over to the original equipment. We want to make sure that you understand that significant figures are not just arbitrary rules, they actually apply to the precision of the equipment that we used. So let's just review the rules, the ones that you learned in 9th grade. Non-zeros are easy because non-zeros literally mean any digit that is not a zero. And any of these numbers that I wrote down from 1 to 9, the not zeros, they are always significant. Similarly, captured zeros are zeros that are between two non-zero numbers. So like we had a 2 here, we had a 4 here. Both of these zeros are captured. Or we have a 1 here and a 4 here. Both of these zeros are captured. You can only capture or trap zeros using non-zero numbers. You can't capture with a decimal. You can't capture with a comma. It has to be non-zero numbers. But anytime you have zeros that are between two numbers that are not zeros, they are captured and they are also significant. Leading zeros are zeros that are before the first non-zero number. So that would be if you have a small number, something that starts with a decimal point. Leading zeros are never significant. Leading zeros are just there because your equipment was of a smaller degree, which means that the actual increments didn't start until after a few decimals. And then you have trailing zeros, and trailing zeros are any zeros that are after the last non-zero. Notice I didn't say after the decimal. They have to be after the last non-zero to be considered trailing zeros. And those are the ones that it's kind of confusing because some of them are and some of them aren't. These trailing zeros are not significant. These trailing zeros are significant. Trailing zeros are only significant if there is a decimal point somewhere in the number. If there's no decimal point written, then they're not significant. So here I had commas, but no decimal point written, so those were not significant. Here, if I looked all the way at the beginning, there was a decimal point, so these trailing zeros are significant. Only significant if there is a decimal, and only the ones after the last number, not the ones directly after the decimal. So if I look at this first number, 1, 2, 3, 4, 5, 6, 7, it was reported to 7 significant figures. But to really confuse things, if all I do is add a decimal into the end of my number, now these become significant, and I would say 10. Quick review, rules state that anytime you're multiplying or dividing numbers, you have to round to the least number of significant figures from the measurements. And anytime you're adding or subtracting numbers, then you have to round to the least precise decimal place. And we'll do some examples of those in the textbook, and I'll definitely give you an answer key for that. But these are the general rules of significant figures. The only one that we're going to add that might be new is when we're taking averages for our labs, we're going to round to the least precise decimal place, or really it's going to be the least precise measurement taken. So again, we're going to tie significant figures over to the measurements that we took, so that if I give you a number like this, 25.0 centimeters, I want you to be able to say, okay, we have two non-zero, we have a 0, but it has a decimal, it's trailing, that would be 3 significant figures. And I would also like you to be able to say, okay, centimeters, that means that we are measuring a distance. We probably used a ruler. And if we assume the last significant figure was our estimated digit, you should be able to tell me the place value of our smallest increments. So here, because this would be the ones place, you should even be able to say, okay, that means that that ruler had a line at 25, a line at 26, a line at 24. It was counting up by ones, which let us estimate that last digit. Where if I said something like 13.2 to 1 milliliters, you would say, okay, we have 4 significant figures. Milliliters measures volume. We can assume the last significant figure was the estimated digit, which means the increments were in the tenths place. So then you should be able to kind of picture in your brain what that graduated cylinder would look like. Our increments were in the tenths place, so we would have had to have had a line at 13.2 and a line at 13.3, and we knew that the meniscus was somewhere between those at the 100th spot. Once you have a better idea of significant figures and how it deals with our precision, the other thing that we're going to just kind of quickly preview for our labs deals with our accuracy and the other definition of precision. So we said this is precision in terms of exactness. We also have precision in terms of reproducibility and our accuracy for correctness. The measurement that I'd like to preview with you deals with these two. And the first type of measurement that we can take, or really calculation we can do to determine how accurate we are, is called a percent error. And this is one thing you'll have to do in lab. Percent error equals, and we're going to take our experimental average minus the accepted value of whatever we were trying to figure out, divided by the accepted value times 100. And if you get a number that is incredibly close to the accepted value for your average, you're going to get a really small number, or maybe even 0 here, in which case you would say that you have 0% error. If you get a number that's really, really far away from the accepted value, then obviously you wind up with a big number here, and you wind up with a big percent error. Positive or negative doesn't matter. If it really makes it better for you, you can absolutely take the absolute value here. But positive or negative doesn't really tell you how bad your data was. It just tells you whether you were too small or too big. A negative percent error just means that your experimental average was smaller. A positive percent error just means that your experimental average was bigger than the accepted. It doesn't matter if you're smaller or bigger, it just is how close to the accepted you are. That's the percent error. Very similar to that would be our precision reproducibility, but there we usually do something called a percent deviation. And in class at some point we'll do an example of this together, but just so you kind of preview it again, if we're looking at our percent deviation, what we actually need to do is figure out each trial, how far it is from the average of our trial. So trial 1 minus average experimental. And then we figure out the same thing for trial 2, trial 3, and again we just keep going for each of the trials that we did. And we get a deviation, or how far each of the trials is from our average experimental value. Once we have all of these answers, we then average those. That's called our average deviation. And once we have our average deviation, we can take the average deviation divided by our average experimental value times 100, and that gives us our percent deviation. And again, we'll do an example of it together once you're in class with me. This is just kind of previewing the form. Oftentimes, when we're doing the deviations, we also take absolute values here so that they don't wind up canceling out, because otherwise you could have 0% deviation even though you weren't at all clustered together in order for reproducibility. So again, today's ideas: accuracy is how correct you are. In order to figure that out, we can compare it to an accepted value, a known value, the correct answer. Precision could be reproducibility, which we would really identify using our deviation to see how far each of our trials deviates from the average of our trials. Notice we didn't use the accepted value there because then it would be accuracy. We want precision. So it's the average of our work from each of the individual trials, and then figuring out how far that represents from the entire average experimental value. but precision can also determine our exactness of our measurements, and that's where significant figures and all the information on significant figures comes from. We will absolutely practice this. We will continue to practice this throughout the entire year because these are pretty big concepts for any science class, but specifically chemistry where we're quantifying so much about our matter. If you have any questions, please absolutely shoot me an email, let me know, and we'll continue to work on it together.